Today we're going to be talking about geologic structures. These are things that are created in the rock after the rock forms. Remember Steno's principle of original horizontality, where sedimentary rocks form flat to begin with? Well, sometimes those sedimentary rocks and other rocks can get bent like this, or maybe like this, or they can get broken. Those are the geologic structures we're going to be talking about today. So these structures are deformation. The synonym for that is strain, and deformation or strain is a change in the size and or shape of the rock. And this is caused by stress. Yes, rocks are under stress, just like we are, except for a rock, stress is a force acting on that rock, and that force is what causes the deformation. And these forces mostly come from plate tectonics, basically the plates moving around and interacting with each other. There are different sorts of stress that act on rocks. You already know one. We learned about this when we went over metamorphic rocks, and that is confining pressure, also known as lithostatic pressure. And this is stress that is equal in all directions, so it is uniform, and what it mostly does is squeeze the rocks together, changing their shape, compressing them, but it doesn't really create structures. Structures are created by differential stress. This is stress that is not equal in all directions. So, for example, you might have compressional stress. Compressional stress is a pushing together stress, and what this is going to do, it is going to shorten and thicken the rocks. This is going to end up happening at convergent plate boundaries, right? Because the plates are pushing against each other. Now there's also what's called tensional stress, and this is a pull-apart stress. And this is the opposite of your compressional, and so it does the opposite thing. It lengthens and thins the rocks, so they get pulled apart and thinner, and this is what you'd expect to have at divergent plate boundaries. The third type of force is called shear stress, and shear stress is parallel forces acting in opposite directions. So basically, the forces are parallel, but they're moving in opposite directions. And this is what you might expect to have at transform plate boundaries, but you do also sometimes see this at convergent plate boundaries. Now, just like there's different kinds of stress, there's also different types of deformation that result from this. And one type of deformation is called elastic deformation. Remember in earthquakes where I had the rubber band and I pulled it and then it returned to its original size and shape when I let go? Well, that's elastic. The whatever was under stress returns to its original size and shape when we remove the stress. But all substances have an elastic limit. If I kept pulling on that rubber band, it would eventually break. And when a rock exceeds its elastic limit, it's going to break, and that's what we call brittle deformation. There is one more type of deformation that can happen, and this is ductile deformation. And this is where the rock bends, but it does not return to the original size and shape when the stress is removed. So we bend it, it doesn't break, it's kind of malleable, and then if we remove that stress, it stays in whatever shape was formed. That's ductile deformation. Now, the type of deformation that happens depends on a number of different things. It's going to depend on how quickly the stress is applied. Typically, if stress is applied very quickly, you tend to have more brittle deformation. If it's slower, you tend to have more ductile deformation. It's also going to depend on heat. Things that are hotter tend to act more ductily than things that are colder, which tend to have more brittle deformation. Now, when these rocks end up getting deformed, They're going to end up getting bent and broken, and those rocks that were originally horizontal are no longer going to be horizontal. They're going to be tilted in different ways. And so we have to be able to describe the tilt of these rocks. And there's some very important reasons for that. For example, if your rocks are tilted this way, it might make landslides more likely to happen in one place than another. Or if we're looking for oil, rocks that are bent like this are a great place to look for oil. Rocks that are bent like this are a terrible place to look. So we want to be able to describe how these rocks are oriented in 3 dimensions. And the way we do this is by taking 2 measurements. The first measurement is strike. It is the compass direction, the azimuth, of a line produced by the intersection of the rock layer and the horizontal surface. Remember in plate tectonics lab, we went over what an azimuth is. It's where we divide directions from 0 to 360 degrees, where 0 is north, 90 is east, 180 is south, and so on. So, for example, right here, there's our horizontal surface. Our rocks are tilted this way. So right there, that is what the strike line would be. It's because it's where those tilted rocks encounter that horizontal surface. Now the second measurement we use to explain how rocks are oriented in 3 dimensions is dip. Dip is the angle of inclination of the rock from horizontal. So if we have horizontal here, the rock is tilted like that, that's the dip. In geology, we use maps all the time, and maps are these nice little flat 2-dimensional things, yet we're describing 3-dimensional rock orientations on there. And so when we use maps and want to describe rocks in 3 dimensions, we use symbols. And the symbol for strike and dip that we use looks like this. So the big line is the strike line. The dip line is the small one. That small one is always at a 90-degree angle to the strike line. So you will never draw strike and dip symbol like that, because that is not 90 degrees. You would draw it like this. And then the last part of that symbol is this number right here, and that's how many degrees the rock is dipping into the ground there. So this tells a geologist that there is a rock that is tilted into the ground at 30 degrees going in that direction. This is normally the part where I'd be asking you guys, are there any questions? And I'm sorry. So hopefully you can figure out this strike and dip and the way we use those symbols to show rocks in 3 dimensions. Now this is an example of a map showing these strike and dip symbols. See, right there, those are all strike and dip symbols. And what we then can use this for in geology is taking this 2-dimensional map and getting a 3-dimensional picture of what's going on. And this is what's called a cross-section. So in this case, the cross-section is going to be cut from A to B. So it's basically like cutting a cake and looking at it on its side and seeing what layers are there. So from A to B, there's A, there's B, here's the Earth's surface. And then we paid careful attention to those symbols there showing the orientation. So these rock layers are tilted 30 degrees from horizontal, tilted into the ground toward A. So we can see what the Earth looks like, not just on the surface, but also underground. And again, this is just another way of showing this, where here's our map view, and there we see those different strike and dip symbols. That helps us figure out that, oh, the rocks are tilted in this direction on this side, but then they're in this direction on this side, and so we can see there's quite some complex structure at that location. So that's how we use these strike and dip symbols to represent our three-dimensional world. So now that we know how to describe the orientation of these rocks in 3 dimensions, let's take a look at some of the structures that are found on Earth. And one type is called a fold. And folds are where rocks are bent as a result of ductile deformation. So when the rocks bend like this or like this and they don't break, well, that's going to create a fold. And folds have parts. Now, if we have this, right, there's my nice fold of paper. These are going to have limbs. The limbs are like the legs, or if it's folded in this way, the arms of the fold. And then we also have the hinge line. Well, the hinge line is the line around which it's folded. And then we also have the axial plane. And a plane is a surface. The axial plane is a surface that cuts the fold in half. And that's what we can see right here. There's our limbs. This would be our hinge line. And then there's the axial plane that slices the fold in two. And what we're showing right here is that that hinge line doesn't have to be horizontal. I tend to fold the paper like this, but you know what? That fold could end up getting tilted in this way or this way. And so that's the hinge line there being tilted. Interestingly enough, that axial plane can also be tilted. It doesn't have to be vertical like this. It can actually get tilted in different directions. So you can have some very complex folds being tilted around in 3 dimensions. Lucky for you, at this level, we don't look at those. We try to keep things relatively simple in this introduction. Okay, so some basic types of folds that we have. First of all, there's an anticline. An anticline has an upward arch. And the oldest rocks of the anticline are going to be in the center part of the fold. So right here we have an anticline, right? These rocks came up. Now these have been eroded, but they come back down around, right? And the oldest rocks will be in the center part of that fold, the younger ones towards the outside. Now the opposite of an anticline is a syncline. In this case, we're going to have a trough shape. So the rocks end up getting shaped like this. And in this trough-shaped fold, the youngest rocks are going to be in the center. So here's a syncline. Our youngest rocks are there in the center of the fold, and the older ones are going to be here in the outside. In most cases, you're going to see that synclines and anticlines form together. So the limb of this syncline is also the limb of that anticline. This also shows you that folds can come in different scales. Some of them can be the size of mountains, and others can be relatively small. Our last type of fold is called a monocline. A monocline is a step-like fold. Basically, you're going to have horizontal rocks here, and you're going to have horizontal rocks here, and then some very steeply tilted rocks in between. Monoclines are relatively common in parts of the western United States. If you drive west of Denver, if you drive around Green River, Utah, and a number of other places, Farmington, New Mexico, you're going to be seeing some of these monoclines like this. Of course, things have to get a little bit more complex than just anticline, syncline, and monocline. Folds, as I said earlier, can be tilted in different ways. The hinge line can be tilted, and so we have to be able to describe these different orientations of the fold. So an upright fold is where the axial plane is vertical. So this is this one that I'm classically showing like that. Axial plane is vertical. Kind of like this syncline right here. The axial plane is vertical in that syncline. But sometimes that axial plane gets tilted a little bit. And then you're going to have an inclined fold where one limb has a steeper dip than the other limb. Oops, I'm breaking my husband's things. All right, so an inclined fold, one limb is going to be steeply dipping and one not so steeply dipping. And that's what we see right here. Coming up here and down there, the axis actually is tilted slightly. You can also have overturned folds, and that's where the rocks in one limb are upside down. So let's say this is the top, right? This fold could end up getting folded so much that what was the top is now upside down. And we can see that right here. Let's say this layer was the top. Well, when we get over to here, it's upside down. So that would be an overturned fold. And then we have a recumbent fold, where the axial plane is actually horizontal. We can often see these where we've had major mountain building events, like here in the Alps. Notice this fold comes around like that. So, is it an anticline or a syncline? Well, we can't really tell unless we figure out the age of the rocks. If we can find out whether the rocks in the center are older or younger, that'll tell us if it's a recumbent anticline or syncline. Now, the last description that we use for folds doesn't refer to its axial plane. In this case, it refers to the hinge line. And this is a plunging fold where this hinge line is not horizontal. So here the hinge line's horizontal. In a plunging fold, it's not going to be horizontal. It's going to be tilted slightly. And how do you tell whether a fold is plunging or non-plunging? You can tell where it's exposed at Earth's surface. So what these little blocks are showing, these are the layers of rock. Each layer has a different color to it. And when you have a non-plunging fold, it's exposed at Earth's surface as these very nice straight outcrop patterns. When you have a plunging fold, it's exposed on Earth's surface with this sort of curved pattern to it. And that's a way to tell whether you have something that is plunging or non-plunging. This is a satellite image showing a plunging fold. We're looking down on this area called Split Mountain, which is at Dinosaur National Monument on the Colorado-Utah border. And right there is the outcropping of rock, and then outcroppings were rocks exposed on Earth's surface. And see that curvature to it? That tells me that's a plunging fold. Now, two very special types of folds are structural domes and structural basins. In all of the previous folds, the rocks either dip towards the hinge line or away from the hinge line. In a structural dome, all of the layers of rock dip away from a point, not a line. And in this case, the oldest rocks are exposed at the center. The opposite of this structural dome is a structural basin. And in this case, all of the rock layers dip towards a central point. And the youngest rocks are exposed in the center. So what we're seeing here in these block diagrams, we have our structural dome here. You can pay careful attention to these little strike and dip symbols indicating all the rocks are dipping away from this central part. Here, this is the basin. There's the center, and you can see all the little strike and dip symbols indicate the rocks are tilted inwards towards that central point. And this is a real structural dome. This is Upheaval Dome in Utah. There's the central point, and all of these rocks are tilted away from that central point. Now, something you might notice, you might look at this and say, but the elevation, the land is lower in the center, so why isn't that a basin? Well, that's because you're not looking at the elevation, you're not looking at how high the rocks are, you're looking at their orientation, you're looking at how they're dipping. And in this case, since all the beds are dipping away from the center, they're going to be a structural dome. So, I don't know, I just put this in here because it looks like a chemistry class, and I don't remember my chemistry classes having unicorns and dragons and rhinoceroses. But anyway, I don't know. I need to take that class. All right, do I sign off now? We'll continue in the next video.